My name's David Castor with EasyPower, and in this webinar we're going to be talking about some additional capabilities in the coordination focus in EasyPower. Just highlight some features and capabilities that it has that might not be readily apparent, and ways we can use it to look at coordination in MCCs and panels, also improve our protection for things like transformers, and talk about our phase and ground faults and how they interrelate, and then finally take a look at Arcflash calculations and how EasyPower, the coordination focus, will allow you to dynamically look at the impact of your settings changes. We'll just do that through some examples here in the book, or in the one line that I have. So first thing we're going to talk about is the ability to do time current curves, or look at time current curves for devices that are within motor control centers and panels. If you're entering the MCC and panel loads in the schedule format that we give you as an option, you can always model the MCC or the panel as just a normal bus in EasyPower. So the other option is to use the MCCs and panels. So over the years, we've added a fair amount of capability to be able to look at coordination for devices that are within the MCC or panel, but it does require that the data be entered in a slightly different way. So we'll take a look at how that's done. So I'm going to go to my little example I have here. We're going to be looking at this switchgear 4, and specifically this MCC 4B here. So this is our symbol for an MCC. Again, you could model the MCC as a bus and show all your loads explicitly on the bus, but you also have the ability to model it as this MCC symbol, and then if we double click on this, we'll see we get this information that's provided with the MCC. So it's a series of tabs, and in terms of coordination, if we look at the incoming tab, the thing that will be of interest is if we define this as having a main breaker, then we will need to define what that main breaker is in order for the program to be able to use its time current curve to display the TCC, and also to do Arcflash calculations utilizing that main breaker if you elect to do that. So that data is entered by clicking this box here, and this is the same dialog that we use for a normal breaker that's shown on the one line. So you will have to define all this information, including the phase trip, in order to get the program to create the time current curve for the main breaker. So the main breaker is one thing that we can show in the time current curve. Then if we go to this description tab, this is actually the tab where we define the loads, the devices that are fed out of the MCC. So historically, we had just basically, we defined a load and the type of load, and then that was really the end of it as far as the model was concerned, the program was concerned. But in order to provide the capability to do time current curves and Arcflash calculations for things downstream of the MCC, we've added the ability to show SubFed devices and also time current curves for components that are within the MCC. So the key to the MCC really entering the loads is this load type. You need to get this selected correctly, and we see you have a lot of options that we've added over the years. So basically anything that says with TCC is going to create a time current curve, or attempt to, if you select this MCC while you're in coordination focus. The default's going to be motor, but if you just enter it as a plain motor, it will know the motor's there, and it will include the short circuit contributions, but it will not draw the motor starting TCC. It will not show the motor circuit protector or breaker that's in the feed, in the starter for that MCC, for that motor. In order to do that, you have to define it as we have here, motor with TCC. And if you select, instead of motor, you select motor with TCC, then when you get down to the motor, you're going to see that these fields here are grayed out. They're gray, and the data is going to appear, but I have to enter the data for the motor using this data button here. So this is going to show me the information for the motor as if I'd put the motor on the MCC. And this will allow me to define the time current curve for the motor. Otherwise, I wouldn't be able to do that. The other thing that's different when you say motor with TCC is you have to define the protected device differently. So again, we see these fields are gray, which means that data is coming from some other source. So again, I need to use the data button. And this is going to be where I define the protective device that I want to use for this motor. And this, once I define this, I have a motor circuit protector here with the 400 amp trip and then instantaneous setting. Once I define all this data, the program will create a time current curve for this MCP. It's just an instantaneous trip only in this case. So that's how we do if we want a motor with TCC. So normally you're going to pick the largest motor that you're starting across the line and use motor with TCC for that. You can have as many motors defined as motor with TCC as you want, but keep in mind that when you select that MCC on the one line and say plot TCC, you're going to get every TCC in that MCC schedule that says with TCC. So you want to use that judiciously, or else you're going to get so many TCCs you're not going to be able to interpret them. They're going to be on top of each other. So the other thing that we have here, let's go back to the one line just for a second. We have this 480 volt panel board, panel 3, that's subfed out of the MCC. Now we could just define that as a load in the MCC schedule, but if we do it that way, we're not going to be able to do any Arcflash calculations for this panel. We're not going to be able to look at the coordination down to the panel board level. So we have the ability, instead of defining it that way, we can define it as a subfed device in that MCC schedule. But the key to that is, before you do that, you need to model this in the one line as we've shown it here. So I have I can just attach to this MCC like it was a bus. So this cable is attached to the MCC, and then at the end of this cable I have the panel board. So now the program understands how this is interconnected, and now I just need to go back into the MCC schedule and define the device that's feeding this panel or protecting it. But the key is you have to put this feeder and the subfed device in first, so before you try to put it in the MCC schedule. So I can also have another MCC that's subfed off of this. I can have multiple devices. I'm not restricted to one subfed device. Okay, so once you put this in the one line, if we go back to the MCC schedule here under the description tab, you see this second row is my panel. And the key there again is defining this load type as a subpanel. And when you do that, these fields here become active, and you're going to define the cable that's going out away from the MCC from the one line, and the subfed device name. You can select from a list here, but in this case it's panel 3. So this defines this is my feeder out to the panel board. So again, because I want to be able to do Arcflash Galax and show my time current curves, I need to enter that breaker data using this data button, which is here, and including all the way down to the phase trip tab, the trip amps, and the instantaneous setting. The program has to have all this data in order to do an accurate Arcflash calculation. All right. So we have other types of things we can show as with TCC, but that gives you an idea of the process you go through. The rest of them will be done in a similar fashion. So we have VFD with time current curves. We have subfed panels, subfed MCCs. So any of those will generate a time current curve. All right, so what happens now if I go to coordination focus, now if you've never looked at coordination in EasyPower, the process is, so right now I'm in database edit. So I'm going to go to coordination focus, which is this button here. And so now I didn't get any error messages, so I'm good to go. So now I'm going to, the general process is you're going to highlight the items that you want to see in your time current curve. So I'm going to pick this feeder breaker, and I'm going to pick the MCC. And we go to plot. So I get a lot of curves, even though I only picked this curve, this device, and the MCC, because of the devices in the MCC that I designated as with MCC and with TCC and the SubFed devices. So let me drag these down. So what we're looking at here is this guy here is the main breaker for the MCC, which is this one we defined in the MCC. The orange curve here is actually the MCP curve. It's just the instantaneous trip. There would also have to be a motor overload relay that we didn't define, but we could, which would come in this, kind of cut this off. This curve is the feeder down to the MCC, so we obviously have some coordination issues here maybe. And then finally, this blue curve is the feeder to that panel, right? This is the panel feeder. The row 2 is the SubFed device, right, that feeds the panel 3. So it shows up because I defined it as a SubFed device, and we defined that breaker information. So again, you can have as many devices inside the MCC defined as with TCC, and they will all show up anytime you pick this MCC and plot it. Okay, so we pretty much provide the capability to do anything you could do directly on the one line. You should be able to do in terms of coordination within the MCC schedule at this point. So it's a little, you just have to enter the data a little differently inside the MCC. And again, let me go back to coordination here. And we'll go back to database. Again, the key is defining the correct load type. So if I want to see a TCC, I can't just say motor. I have to say motor with TCC. And also for the SubFed devices, you have to define those on the one line first before you try to enter them in the schedule here. So I did get a question that was sent in, is it possible to combine the overload relay curve and the MCP curve on a TCC? And the answer is yes. So if you look at, go back and look at that breaker data here. So here's my motor with TCC on row 3. If I go to its protected device, the motor overload data is actually a separate tab under the breaker data. So if I were to select this motor overload tab, I could say plot motor overload relay TCC, and I would define all of the parameters associated with that. It has to be something in the library, obviously, but if I do that, and I'm not going to do it now just because I don't have all the data worked out off the top of my head, if you define the motor overload relay, what will happen is it will be combined with the MCP curve, and it will actually cut off the top of the instantaneous trip curve and show the two as one curve. So that can be done. If you just have to go in and enter that data. The only tricky bit is remembering that it's actually the motor overload data is part of the breaker data. All right, so that's just a little overview of the coordination capabilities and Arcflash Galax that we have for MCCs and panels. So if I were to go back to coordination now and fault this bus, you'll see that I do get an Arcflash result for this panel. If I had just entered the panel as a load in the MCC schedule and not shown it on the MCC, I don't have a way to get this Arcflash calculation. So That's the other reason that we do it this way. Okay. All right, so next thing I want to talk about a little bit is kind of under the general topic of enhancing system protection. We'll talk about setting instantaneous trip elements and the information the program can provide to help you do that. So in general, the way that we coordinate inverse time overcurrent elements in a system is to make the upstream device slower than the downstream device. So when you put a lot of these in series, the upstream device gets very slow, regardless of where the fault is. Now, if we had instantaneous trips, that would be much faster and would give us much better protection. But in general, when I have two instantaneous trips in series, there's a high risk that those are not going to coordinate. But if we do have a lot of impedance between those two overcurrent devices, instantaneous trips, I can use that fact to coordinate the instantaneous because I have less fault current downstream of that impedance. So utility engineers will talk about the reach of an overcurrent relay as far as how far down the transmission line or the distribution line will that overcurrent relay see a fault. So we can utilize the same concept when we look at transformer protection. So if we set our instantaneous trip correctly on the primary side, we can use it and we'll still coordinate with the downstream side. So we'll take a look at how you do that and the information that the program can give us. So let me go back to my little example here and go over to the switchgear 7, I think. So I have this transformer 7 is fed by a circuit breaker, 13.8 kV circuit breaker and a Basler 851 multifunction overcurrent relay. And so let's just we'll take a look at what the coordination looks like at this point. So I'm just going to keep it simple here, I hope. And oops. We'll take a quick look at the coordination of, we'll look at the main and then maybe this big breaker here. So now when I go to plot, it's going to plot these curves for me. So let me just drag some notes around here. The program doesn't always get them exactly where I want them anyway, so you can drag these around just like text notes. All right, so here's my relay curve, and it's strictly an inverse time, very inverse. So inverse just means the higher the fault current, the faster it operates. So this looks pretty good. It coordinates with my downstream 480 volt devices. But if I had a fault out in here someplace, it's still going to take a certain amount of time to operate. So this is 0.2 of a second here. So that's a fairly slow operation if I had a major transformer fault. So remember, this relay is up on the primary side of the transformer. So it's looking through the transformer. So one of the things you can think about is if I look at my half-cycle fault current down here, I have 39,000 amps of fault current, of which 28,044 amps are coming down through the transformer. The rest is motor contribution. That translates to 1,000 amps going through this into the primary of the transformer for a secondary fault. So basically, if you think about it, I can come up here and I have remote voltage and current I can display if I right click. I've got the same 1,000 amps going through this CT. If this relay sees fault current that exceeds the 1000 amps, what does that tell us about where the fault is? Well, if that fault current exceeds this 1000 amps, the fault really has to be either in the transformer or on the primary side. Because remember, this transformer is a substantial impedance in my system. So if I fault this bus, I get 18,000 amps going through that relay on the primary. If I fault on the secondary side, it's 1,000 amps. So it's almost a 20-to-1 ratio, which is roughly where you're at on the impedance, right? So we can use that fact to set an instantaneous trip on the primary protection here, knowing that if the current exceeds a certain value, the fault can't possibly be on the low side because of the impedance of the transformer, and I can trip on instantaneous without waiting for anything. And you can see how EasyPower actually stops the curves because I faulted a single bus. It stops the curve at that maximum fault current. All right, so there's one other complication, and that is we have to look at symmetrical versus asymmetrical current. And so in general, what we are displaying here is going to be symmetrical, RMS symmetrical current. But some overcurrent devices are sensitive to the asymmetrical current, some of the instantaneous trip elements. The newer relays like this one will have what they call a DC offset filter, which means it will not respond to the asymmetrical portion of the current. But that you have to look at that on a case-by-case basis. So if I close the TCC just for a second, just want to show you, I got to change my options here real quickly. If I go to short circuit options to one line output, I can display both the symmetrical and the asymmetrical. So the asymmetrical is going to show up with parentheses around it in kiloamps. So if I do that, you can just get an idea here. So I'm going to fault this bus, and I got to change back to half cycle. Okay, so here's my 39,000 amps of bolted fault current, but this is RMS. The maximum asymmetrical current based on the X over R ratio of the system, looking back in from this point, I get a maximum possible of 50,650. So as far as what's going through on the primary side, I have 1,000 amps symmetrical and 1,110 amps asymmetrical. And I should see the same thing here. Okay, so here's what the relay is seeing, maximum asymmetrical. So in the old days, we would use a safety factor. We'd multiply the symmetrical by 1.6 and add another 10% onto that and set the instantaneous up there. But with EasyPower, it can tell you give you a much better approximation of the X over R, of the asymmetrical current, because it knows the system X over R ratio. So you can use this value. So you would set your instantaneous trip above this maximum asymmetrical current if the device responded to asymmetrical current. So if I look at the database information for this relay, you'll see there's a comment here. It says relay has a DC offset filter, and we track this in the database. Now this is based on what the manufacturer tells us. So what this means is, in theory, you could ignore the asymmetrical current for this particular relay, just use a symmetrical current. So older electromechanical type relays will be sensitive to the asymmetrical current, so you'd want to take that into account. Also, molded case circuit breakers, the instantaneous trips on those are sensitive to asymmetrical current. So if we wanted to set the instantaneous for this transformer primary relay, we can go back to my time current curve I'll recreate here. Yeah, we'll go down. This guy and this one. All right, so what I'm going to do is double click on this curve to get my data. And the phase overcurrent is function 1, so that's going to be this one. I'm going to go to settings and then make sure I'm on function ID 1. So here's my time overcurrent settings. I have tap 2, vary inverse, time dial 1.2. And down here is my instantaneous. Right now it's disabled. So to turn that on, I just change this. I have to set a range. In this case, it's 0.5 to 9.99. And I have to pick a setting. So this is in terms of primary amps, I think. I have to remember. One of the nice things is you can just make a guess here. Yeah, so this is in primary amps. So if I want 1100 amps, so let's say I take, I use the symmetrical current of 1100 amps through the primary for a secondary fault. I got my calculator out, can't see that, but I got 1200, that's 1200 amps if I allow 10%, right? So the CT ratio is 800 to 5, which is 160. So that's going to be about 7.5 amps. So if I say 7.8, then I get 1248. The program tells you the actual primary amps down here. So that's a good place to check to make sure you're understanding how the tap setting relates to actual primary current, because that's going to vary between manufacturers. If it's a Schweitzer relay, it works one way. If it's a multi-lin relay, it works another way. We mimic that in the way that the relay is modeled in the program. Okay, so now I'm going to set my instantaneous trip at, I will make it 7.7. And now I get this line here. So this is my instantaneous trip function. This is saying anytime the primary current exceeds this value, this relay is going to trip on instantaneous. So you can see it's going to be much, much faster for these faults up in this region. Before it was like 0.2 seconds. Now it's going to be, however long maybe a cycle for the relay to operate and 4 or 5 cycles for the breaker to trip. So it improves your transformer protection pretty significantly at really no cost. You're going to get this instantaneous element whether you want it or not when you buy that relay. So if in terms of formatting the TCCs, just a note, anytime you double click on a curve, you're going to bring up the data associated with that protective data. There's going to be an appearance tab. If I check on that, I can change the weight of that line. Just for relays, sometimes that's helpful. I do that for demonstration purposes. So here's my curve. You can see it doesn't actually coordinate with the main because they're trying to protect the transformer damage curve for that delta Y transformer. That can be problematic, but that's just something they decided they could live with. If you really wanted to coordinate this with the main, you'd have to increase this tap setting here a bit. But now we've added the instantaneous strip. So this is going to operate even more quickly than the fuse in this case for the high magnitude fault. So here's my maximum fault currents way out here on the primary side. So if I have a primary cable fault or something like that, this is going to trip much more quickly and limit the damage, basically. So that's the advantage of the instantaneous trip, and shows how we can use the information in the program to give us the information that we need to set that accurately. So remember that asymmetrical current needs to be considered if your primary device is sensitive to the DC offset current. And the program will try to tell you for the relays if it has a DC offset filter or not. All right, so just remember the TCCs are interactive. So if I fault a single bus, these TCCs get clipped and the fault arrows move depending on the magnitude of current through each device for any particular bus fault location. So you can see for a fault down here, this is not tripping on instantaneous because there's not enough current going through it. So that just confirms that our settings were conservative enough, and this should not trip for a secondary fault, which is what we want. And so something downstream will clear it before the primary relay trips. Okay, so next topic is going to be to talk a little bit about ground coordination and the relationship of phase and ground. So typically when we do look at our coordination and draw the TCCs, our circuit breaker, multi-case breakers, and low voltage power circuit breakers, we're generally always looking at fuses. Mostly we're looking at phase overcurrents. So when we start talking about ground faults, then we have to make sure we define those settings in the program so we can display those TCCs if we want to look at them. So we'll take a look at how we do that and go back to database real quick here. All right, so if I look at it, let's look at this main breaker here. If I double click on this. So this specification tab defines the breaker type and the frame basically. And the trip unit type doesn't tell us what the settings are. To enter the settings, we go to the phase trip tab, and this box will always be checked by default. And these are our phase trip settings. So if I buy a 480 volt circuit breaker, it has to have a phase overcurrent. I can't buy one without it. So this will always be something you have, whether it's a thermomagnetic breaker or a solid state trip like this one. So these are my phase overcurrent settings. Now if it does have ground trip, you'll need to enter that information separately. And to do that, you go to the ground trip tab. This is for low voltage breakers. If I go there, when you first open it, this box will not be checked. In this case, I've already gone in and defined these settings. So here's the plot ground TCC tab. And once I check that, then I need to go down and enter the settings. It's pretty simple for these 480 volt trip units. I have a pickup setting, I squared T in or out, and then I have a delay. So we generally coordinate the ground faults through their delay settings. And so the main typically will set it max, and downstream breakers you'll set it intermediate or minimum. So you would have to go through and set all these for all the devices where you have ground fault. Okay. So I've done that for these breakers here in this substation. So if I go back to coordination now and we take a look at this, let me just go up here real quick. And I'll just look at one because those are basically all the same. If I go to plot, then I don't see my ground TCCs, and this confuses people sometimes. But remember just before I showed you the TCC clipping, the fact that when I do a calculation or plot a TCC, the program figures out the maximum fault current through each device and clips the curve at that maximum current. But by default, whenever I create a TCC, it's based on a three-phase fault. And so if I have a balanced fault, three-phase fault, there will be no ground fault current. And the only thing the ground trip is sensitive to is ground fault current. So there's zero current, so all these devices are being clipped at 0 amps. So they don't show up on my one line. if I have an option here to change this from phase coordination to ground coordination. If I click that, then it changes it from a line to ground, from a three-phase fault to a line to ground, and now I see all of the devices that are sensitive to ground fault current only. So here I have, this is my main breaker and this is my feeder, right? So these are coordinated pretty much based on time. And these do coordinate. There's a little bit of space between the two, so those will coordinate. Now, the other thing that we still see is this fuse curve. So why are we seeing a fuse curve on a ground trip? Well, the main reason is that this fuse is on the primary side. This is a delta Y transformer. So this ground fault on the 480 volt side looks like a phase fault. But by switching this, it's going to look at ground faults on both sides. So I see both curves. All right, so this is how we look at the ground fault. Again, you're going to switch this up here between phase and ground. Okay. You have to be a little bit careful in interpreting coordination if you look only at ground fault, because somewhere downstream there's going to be a phase overcurrent device that sees the same fault. And so there can be a need to coordinate between phase and ground devices. So you have to be aware of that as well. Of course, the advantage of the ground fault protection is that it doesn't see load current, normal load current. It'll see if you have some imbalance if you don't compensate for that. But in general, it doesn't see load current, so it can be more sensitive. The phase overcurrent devices have to be able to handle the full load amps so it doesn't trip on load current. So the advantage of ground fault is that it can be more sensitive. So let me go back. So just remember, you have to define those settings, though, before you're going to see the curves. But let me just look at the main, and we'll look at, I don't know, let me come down here and look at this feeder. And if I change this to ground now, if I had a small phase overcurrent device downstream here, and I have a ground fault, one of those three phases is going to see that ground fault. So at some point, as this device gets really large, it's not going to coordinate with your upstream ground fault. So let's see. I thought I had another example here. Hang on. Oh, here it is. Let's take a look at this guy. So this curve here is the main breaker for MCC 7A. And if I change this to ground, here's my ground curves we looked at before. I want to look at how this upstream ground protection is going to coordinate with that main breaker. So I can change this to say view phase and ground. Change this to line to ground. So now I can see the phase and the ground. And it's a little bit confusing, but here's my main breaker. And you can see if I have a fault in this region up here where I'm on the thermal curve of this main, the ground devices are going to trip before that phase overcurrent device, which is really not what you want. And if I didn't have ground on this, then it would really miscoordinate, because I'm going to trip the main breaker up here on the switchgear for a ground fault down in the MCC somewhere, because this main is going to be slower in that range of fault current. So the smaller phase overcurrent breaker devices, the small molded case breakers, will generally coordinate with these ground protection devices, but you'll reach a point where the size of this breaker is too large. It's not going to coordinate with this ground fault unless you provide ground fault protection down here. So now the NEC requires ground fault protection only on the main device above 1,000 amps or whatever it is. That's more just a fire protection issue, right? The NEC doesn't, in general, require that things coordinate except for emergency power these days. But so if you are trying to spend the least amount of money, you'll put a ground fault device only on the main, and you won't put ground fault on the feeders, and then becomes a bigger coordination problem, because now for a ground fault down here, you're at risk of losing the entire system. Or that's completely preventable if you put ground fault on these feeders for that small additional cost. All right, so just remember, if you're not seeing your ground fault curves, make sure you're on a line to ground fault, because on a three-phase fault, they're not going to show up on your time current curve. All right. So our last topic, we just want to touch briefly on Arcflash calculations and the time current curves and some of the tools that you have to look at that. The main thing you have is the ability to look at this Arcflash results with the time current curve and see the changes to the Arcflash results as you adjust the curves. So if I go to my my same substation here, I can remember which one I was looking at before. Let's look at this situation here. So if I wanted to look at the Arcflash down at MCC 7B, well, first of all, if I just calculate Arcflash down here, I get 97 calories, but it doesn't really tell me exactly what's going on. So if we now would go to the, it doesn't tell me why it's so high, if there's anything I can do about it. But now if I go to my time current curve, I can do the same Arcflash calculation. Oops, if I could use a mouse, I could. All right, so this one line we show you in the time current curve, this is a live piece of the one line, has its own coordinate system, so I can rearrange this. It doesn't bother the other one line, the main one line. And I can also look at Arcflash results, okay? So the nice thing about this is interactive. So this is my breaker curve, trip unit curve for this BL7D. So this is my short time trip. This vertical line is my short time pickup, long time delay, and my long time pickup. So let's see what happens if we reduce the short time pickup setting. Right now it's at 7, and I can drag this in EasyPower. Just hold down the left mouse button and drag this setting. So you can see it recalculated. When I lowered it 1 notch, it went from 97 to 9. And the reason for that is I'm catching the Arcflash arcing current in the short time trip. Before it was tripping on the long time, the thermal. Now it's tripping on short time, so it's much faster. So I've speeded up the operation. And if we went back and looked at the Arcflash report, you would see a big decrease in the arc time. I can prove that by adjusting the short time delay here. So if I increase this, you see the Arcflash is going up again. So this is dynamically recalculated on the fly as I adjust these settings. So that's a huge advantage when you're doing Arcflash studies. Okay. So you just have to look at your coordination with other devices, obviously, but in general, you can see what you can do to lower the arc flash by adjusting these settings. The other thing I want to look at was the how to display the arcing current on the TCC. So if I wanted to see where the calculated, remember the arcing current has to be calculated using the IEEE 1584 equations, and that's always going to be less than the voltage fault current, the normal half cycle, and at 480 volts it's a lot less. So if I wanted to see what the arcing current was, I can display that on the TCC by first I highlight the device that's tripping. That's the only kind of tricky part. You first have to highlight the curve that's tripping, that's the fastest upstream device that's giving you this result. And if I right click on this, it's going to say insert arcing current tick mark. And then I get this little triangle down here. Let me pull it up. Okay. So this shows me for this bus, it only works for if you have one bus faulted. This is my arcing current tick mark. So if the time, arc time is going to be the time it takes to get to the top of this, which is just under 0.2 seconds. So that's going to be my arc time. Now, if you try to display this and you get an error, it says you didn't, most likely cause is you didn't pick the device that's actually tripping for this fault. So you got to make sure you pick the right device. And it will automatically switch between the 100% and 85% depending on which is the worst case. So I guess the other thing this shows is the impact of somebody making a settings change that you are not aware of. So, if this thing trips for some reason and somebody goes out in the field and cranks it up one notch, what could that hurt? I went to short time pickup of 5 to 7, but my arc flash went from 9 calories to almost 100 calories. So settings changes have a big impact on arc flash, or at least they can. So something to be aware of. All right, so that just highlight a few things, capabilities, and the coordination focus power protector. All right, so I want to thank everybody for sitting in today, and don't forget to come back in the future. We'll have additional webinars. If you have topics you'd like to see covered, then let me know, and or send a comment to Nicole at EasyPower, and we'll see if we can provide a webinar for that topic. So anyway, thanks everybody, and we'll talk to you again soon.